Well, greetings, mathletes, and welcome back. So we've been spending a lot of time taking derivatives and learning how to take derivatives and techniques for taking derivatives, but today we're actually going to do something with those derivatives other than find more derivatives. So what we're going to be looking at today are extreme function values. Now, an extreme value, it's probably exactly what you think it is. It's either the largest or the smallest value of a function on a particular interval, right? A closed interval particularly. In any case, let's go ahead and get started because we have some definitions and theorems to talk about, and then we'll get down to the mechanics of how we actually do this. So let's go ahead and get started here. There we go. And so we're going to be focusing on extreme values on a closed interval. So, well, I always do that. There we go. And so Extrema on a closed interval. And by a closed interval, it's basically an interval from A to B where you include the endpoints. Okay. Now, a little bit of Latin grammar. When we talk about a maximum or a minimum, that is singular. And in normal English, you would say maximums or minimums, and I suppose you can here, but generally that's not how it's done. So let's look at this real quick. Singular, plural. Just quick rundown. So singular would be minimum. Plural would be minima. Right? And that's just the way you pluralize things in Latin. Maximum. Oops. The plural, boy, I'm having real spelling issues anymore. Boy, I picked the right major, didn't I? So maxima would be the plural. And, well, you already see the plural of extremum, right? And extremum is the singular, and extrema is the plural. And that's just so you understand, because I'm going to be using all of these words rather interchangeably. Well, not too interchangeably, but rather fluidly. And I just want to make sure we understand that they really are the same words. Minima is just the plural. It just means more than one minimum. Okay. Now, there are two types of extrema. So types, you have local, or sometimes, well, your book tends to call them relative. Right? So you have local or relative extrema, and then you have global or absolute. Right? If it's local, what it means is that it is a maximum or a minimum, but only in the area that it's in. So let's get an idea of what these things look like here. So let's just say I have a function here, and I'm not going to put any numbers on this. But I on a closed interval, let's go from A and go up here, and let's say B is right here. Okay, just so we understand what the differences are. Oh, and actually, let's do this just for fun. I'm going to change this last part a little bit. Let's drop this down to here. Okay, now, when we're when you're talking about a local or a relative minimum or maximum, what that means is that it may not be a maximum over the entire interval from A to B, but it is bigger than everything around it. right? At least there's some area around it that you can carve out where you can say, yes, this is the biggest value. So for example, here, right, that is not the biggest value in the entire function, right? This is the biggest value in the entire function over this domain. However, this is bigger than everything around it. It's bigger than all of these values on the left, and it's bigger than all these values on the right. So it may not be the biggest, the largest value in the entire function, but it is the largest value in its neighborhood. And that's actually a math term, a neighborhood, and your book isn't using it yet, but a neighborhood is just there's some interval around that point, right? And it can be any size as long as you can find you can find a size that makes it the biggest. Then it is a local or relative maximum or minimum. So this one is local. This one's bigger than everything, so it's global, right? So this one is a local max. This is an absolute max or global max. Over here, I have a minimum here and a minimum here. This one would be absolute or global. This one would be local or relative. Right? And so it's just, as far as the pictures go, it's just a matter of telling those two things apart. Let's go ahead and look at another one here just to kind of get an idea of what these things look like. Let me do this. I'm just going to erase the whole thing. Okay. You could have something that looks like this. Right? Let's say we have... and we'll have an open circle there, and then we have that, and an open circle there, and I have just a dot here. If I look at this function, and if this is from A to B, right, that this is A and this is B, if I look at this now, I don't have any extrema in this. This looks like it's heading up towards a maximum, right? But there's no value there. The limit exists, but the function isn't continuous, right? This is actually a counterexample I shouldn't say a counterexample. This is an example of why the function has to be continuous. There we go. That's what I was trying to say. This is why the function has to be continuous for this theorem to hold. If there are discontinuities anywhere in the function, you can have a situation where there are no global maxes and no global minimums. If you have a continuous function, you're always guaranteed to have at least a global maximum and a global minimum. So, yeah, looking at these, I don't even have any relative maxes or mins, right? Because if I look at this, well, I suppose that could be, let's see, this one right here is, we can actually carve out a neighborhood here where I can say I have a local minimum, because this value here at A is 0, and that's smaller than all the function values around it. This one here is a local max or a local maximum because it's bigger than everything that's just around it, but there are no global maxes and mins here. So I have a local max and I have a local min, but that's it. I don't have anything global. If you're going to guarantee that it's going to be a global max or a global min, you have to have a continuous function. There may be a global max or global min, but to guarantee it, it has to be continuous. Okay, so let's go ahead and get rid of that, and we'll start looking at some examples here. Okay, so our goal is going to be basically this. If we're given a function, right, we're given some function f, let's, yeah, right, f of x equals blah, 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 whatever. I'm not going to if I know if I put an expression in there, it's going to focus. You're going to focus too much on the expression. And you'll be given an interval, a closed interval from A to B, right? And A and B will be numbers, or it could be given to you this way. But either way, you're going to be given an interval. What you need to do is find the global or the relative, or not relative, global or absolute extrema of this function, right? Whatever it happens to be. And so, when you look at a function, we know that the extrema of a function, they could be local extrema, or or it could be an endpoint, right? An endpoint could be an extremum as well. So, if you look at these local extrema, I'm just going to make something up. We'll pretend this function continues off in some other direction or whatever. If we look at the slope of this thing, right? As I approach this extreme value here, this local extreme, if we think about what happens to the slope, where the function value is greatest, the slope is 0, right? So whatever this value is at C, f prime of C is equal to 0. Okay, you notice that's a derivative, right? And the derivative tells you what the slope is. So anywhere there's a local maximum or a local minimum, there will be a 0 derivative at that point. Now, that doesn't work in reverse. Just because you have a 0 derivative does not mean it's an extrema. That's something that you have to check, and we'll talk about how to check that here in a second. So all of these points, any point C such that f prime of C is equal to 0 or is undefined is a critical point. Okay. Any extrema that is not an endpoint will show up in your list of critical points. Now, you could have critical points that are not extrema. For example, when you look at the graph of x cubed, and we will be looking at it a little bit later, that point right there at the origin, this point right here, it actually turns out that the derivative there is 0. But this is not a maximum or a minimum, right? It is neither, not local, not global, not anything. It's just another value. So that would be a critical point, but it is not an extrema. So you have to be real careful here. It's real easy to accidentally label the wrong thing. So let's look at the whole procedure, and then we'll walk through an example. I'll do that, and I'll get this off here. Oh, that's not what I meant to do. Let's do that again. I'll just do this. Boy, I'm having all kinds of issues here. My fingers aren't hitting the hotkeys right. There we go. Okay. To find global or absolute, your book calls it absolute more often. Okay, so we want to find global or absolute extrema on a closed interval. Okay, so 1, list the endpoints. 2, solve f prime of 0. Oh, excuse me, not f prime of 0. F prime of x equals 0. And you want to solve those for x values. And then you want to take, so you want then to evaluate all points from steps 1 and 2 and pick the biggest and smallest. Right? It's actually pretty straightforward. You check the endpoints of the interval, then you set the derivative equal to 0, solve for those critical points, right? And then you check endpoints and critical points, and whichever the biggest one of that list is your global maximum, and whatever the smallest one on that list is your global minimum. And that's the whole process. The biggest problem comes in right here. You have to know how to take derivatives to be able to do this process, right? So you take the derivative and then you set the derivative equal to 0 and you go from there. Okay, so let's actually walk through this process. Okay, so suppose our function is f of x is equal to x cubed minus 3x minus 5, right? So that's our function. Now, what's nice is that we know that this is continuous over its domain, right? Because it's a polynomial and all polynomials are continuous. The interval we'll be given is from -2 to 3, right? So what that means is that we are on the interval from -2 to 3, right? So that's what we're going to be dealing with. So we know, first of all, right, we have points to check. And we'll just get a list going. So x equals, let's see here, we got -2 and 3. Those are our endpoints. That's always on our list. We always check the endpoints. Now, we need to find f prime and set it equal to 0. So the derivative of this polynomial would be 3x squared minus 3, right? So now we have 3x squared minus 3 equals 0. Well, let's go ahead and take a look at this. Let's see here. I can divide everyone by 3, and that gives me x squared minus 1 is equal to 0, and that factors, so it's x plus 1, x minus 1 equals 0, which means that x is equal to 1 or -1. So we can add those to the list, -1 and 1. It doesn't have to be in a particular order. I think I just reflexively write the -1 first. Right? So we have 4 points to check. These are our critical points, right? Because those points make the derivative equal to 0. They don't make it undefined, but that could happen too. And so we have 4 things to check. So we're going to be taking these points and plugging them back into this function and seeing what their function values are. And then the biggest one is going to be our global maximum, and the smallest one will be our global minimum. Okay, so let's see. F of 2, or f of -2. Let's see, -2 cubed is -8. I'm just going to kind of scratch this stuff out on the side. So -8 plus 6 minus 5. Is that right? Yeah. So let's see here. That would be minus 13. That's 7. -7. So we have the point -2, -7 is our first point. Now we're going to plug in 3. And I'm just kind of using this for scratch here. So I have 27, because that's 3 cubed, minus 9, minus 5. Okay, and let's see, that would make it 13. Okay, and now let's check our critical points. So those are the endpoints. F of -1 would be -1 cubed is -1 plus 3 minus 5. So it's negative 6 plus 3, so that's negative 3. And we need f of 1 now. And then we're just going to compare these values and figure out which one's biggest, which one's smallest. If I plug in 1, I end up with 1 minus 3 minus 5, which is negative 7 again. Okay, so once we've done all that, we just have to rank these. Now, as far as the biggest values go, this is our absolute max. Now, we have two values that are the same for our minimum, right? Negative 7 is smaller than negative 3, but I have two negative 7s. And so even though they are the same value, they are still considered an absolute maximum, each one of them. Or excuse me, absolute minimum. I said that backwards. I think typically what will happen, though, is that you'll just have one of each. But you absolutely could have two, right? There's no issues there. But it's really just a matter of picking your largest and smallest values. And that will tell you your global max and your global min. So you evaluate at the endpoints, and then you evaluate at critical points. And critical points are places where the derivative is either equal to 0 or it's undefined. Okay, so let's take a look at another example. Okay, so this time let's go ahead and take a look at the square, f of x is the square root of x, and we'll look at that on the interval from 0 to, let's say, 4, right, because we feel crazy. Okay, so we want to find the global maximum and the global minimum. So we have the endpoints first. So the points we're going to check, we have x is 0, x is 4, and now we just need to take the derivative and figure out what our critical points are. So we want f prime of x. Let's see here, and x square root of x can be written as x to the 1/2, so I'll look at it that way. If I do that, I end up with 1 over 2 times the square root of x is what it ends up being. I just used the power rule and converted it back to a square root. If I set that equal to 0, right? Yeah, you notice we have a problem here. This is never equal to 0, ever. However, if you look at this, this does have one value that's undefined, right? And x equals 0 is undefined. Now, if x equals 0 is undefined, that makes it a critical point also. So x is a critical point. It's already on our list. Okay, looks like we just have two things to check now. Now, in your mind, it's always a really good idea to have an idea of what these graphs look like. If I look at this, right, from 0 to 4, it's pretty obvious from here that the endpoints are your maximum and minimum. So you can actually jump to the answer if you know something about the function ahead of time. You notice, just looking at this, there's no need to take a derivative, right? There really isn't. If you understand the geometry of the curve, you don't need to take a derivative. But it's a good idea to do it anyways. So let's evaluate our endpoints. So f of 0 is 0, and f of 4 is 2. So this is our minimum. This, I should say, absolute. And this is our absolute max over that interval. And some of this stuff is pretty straightforward. Some of it gets a little I don't know, twisted. And other times it's just hard to picture what you're working on. And when it's hard to picture what you're working on, well, it actually gets very confusing. So being able to picture it is actually a good idea. Okay, so let's look at another example. Okay, so for last example here, let's look at f of x is equal to sine x, where, let's see, what did I decide the endpoints were? From negative pi over 2 up to 5 pi over 2. Oh, excuse me, 5 pi over 6. Okay, so we know the sine curve, right? We've been messing around with it for a few semesters now, ever since trig. So let's go ahead and sketch it in and look at what those endpoints are actually telling us. So let's see, sine curve does one of these. We'll just pretend this is a smooth curve. Let's see, it goes to 2 pi. That's pi, so that would be pi over 2. And that would be 3 pi over 2. Okay, so we have that. Oh, wait a second. This is negative. That means we have to go out to at least negative pi. Yeesh. I wonder if I can just, yeah, I can, good. Well, we'll just pretend that's a good curve. And negative pi over 2 would be right here. So we're actually looking at this curve from here. Wait, 5 pi over 6? Well, let's see, where does that have to be? Let's see, if it were 6 pi over 6, that would make it pi, right? Because the 6's would cancel. So that means that this is a little bit less than pi. So it's about right here, right? And I'll just put this down here, 5 pi over 6. So we are looking at this curve between these 2 points, from here up to here. So we can actually forget about everything else. Now, so we know that points that we have to evaluate are endpoints, and we just have to figure out if there's anything else in there. Now, a lot of the time, you can look at it and figure out where those peaks are, right? For example, I can see there's a peak right here at pi over 2. I can see there's a trough here at negative pi over 2, and that's just because we know the function. But if we go ahead and follow the system, f prime of x is the derivative of sine, which is cosine, and what we need to do is figure out where cosine is equal to 0 or undefined. Now we know cosine is never undefined. It's defined everywhere. So that means we just need to figure out where cosine is equal to 0. So if you wanted to, you could just sketch out a cosine curve. In fact, that's how most of the, that's how it's mapped out most of the time. And we know that at pi over 2, it crosses the x-axis, and it does it again at negative pi over 2, right? And that's everything on this interval. So the interval that takes it up to, what do you call it? Boy, I can't think today. The interval that takes it up to 5 pi over 6, those are all the zeros that's in that interval. So negative pi over 2 is already on our list, so we just need to add pi over 2. So those are all the points we need to check. So we need to look at f of negative pi over 2, which is sine of pi over 2. And excuse me, sine of pi over 2 is 1. Then we need sine of negative pi over 2, which is negative 1. And sine of 5 pi over 6. Now, since this distance right here, I mean, you can always go back to your unit circle and just look at it. But I'm going to show you how I'm thinking about it. It is pi over 6 short of pi. That's how far it has to go to get to pi. So that means it has the same value over here as it does at pi over 6. Right? These two values will be the same. And sine of pi over 6 is 1/2. So sine of 5 pi over 6 is also 1/2. And again, look at your unit circle if you need to get these values, if nothing else. It really does help. Okay, so looking at these, now we can decide which ones are global maxes and mins. And you're going to have to forgive the gardening crew outside for the moment. So looking at these, this is our largest value, so this is our global max. And this is the smallest value, so this is the global min, right? So those are our two values. So I have a global max at x equals pi over 2, and I have a global min at x equals negative pi over 2. Right? This ends up not really playing into it. It is a local maximum on that interval, but it is not what we were looking for at the time. All right. So that's the last example. And really what I want you guys to remember is it's always the same steps. You check the endpoints, and then you take the derivative to find your critical points. So the critical points are either where the derivative is undefined, so you're dividing by 0, or the derivative is equal to 0, right? Those are your critical points. So you find all of those on your interval, check everything. The biggest one is the max, smallest one's the min. It's real straightforward as far as that goes. The tricky part is taking the derivative. So in any case, until next time, keep your pencils and your wits sharp.